Hello student, now we are going to start another chapter, that is oxygen transport in arterial blood. So in this chapter what we are going to learn, we are first going to understand what are the different methods of oxygen transport in arterial blood, and under this session we are going to understand how to calculate the dissolved oxygen in the blood and how to calculate the oxygen combined with hemoglobin. So these are the two forms by which the oxygen transport occurs in arterial blood. And then we are going to learn another main important topic, that is oxygen hemoglobin dissociation curve. Here we are going to learn what are the causes of the right shift, what are the causes of the left shift of this OHDC, and also we are going to understand what is the role of 2,3-DPG on OHDC. And at the end of this session we are going to understand or discuss few MCQs. So this is our plan. Now let's start with the first topic, that is methods of oxygen transport. So oxygen transport in arterial blood. Before starting the topic, I will ask you, please try to recall that in the last session we have discussed that the partial pressure of oxygen in the atmosphere is 160 millimeter of mercury. When this oxygen enter inside your conducting zone of the lung, that is the inspiratory oxygen, the partial pressure here is 150 millimeter of mercury, and when the same oxygen is entering at the level of alveoli, the partial pressure of that oxygen is 100 to 104 millimeter of mercury, that we have already discussed. So the venous blood which is entering in this alveoli, right, it has a partial pressure of oxygen which is 40 millimeter of mercury. So after entering into this alveoli, the oxygen exchange is going to happen, and here there will be equilibrium of the partial pressure of oxygen with that of the alveoli. So if the alveolar partial pressure of oxygen, the capillary blood will also have the same partial pressure. But I told you in last class also that whenever you calculate the partial pressure of oxygen in the arterial blood, that is not exactly 100, that is around 95 to 98 millimeter of mercury, and that is due to physiological shunt. Now in today's class we are going to understand that with a partial pressure of 95 to 98 millimeter of mercury, how the oxygen is transported at the level of this arterial blood. So what are the methods of oxygen transport at the level of arterial blood when the partial pressure of oxygen in the arterial blood is 98 millimeter of mercury. So this is today's class discussion. So first of all, we are going to understand what are the different methods of oxygen transport in arterial blood. There are two dominant methods. Obviously, one is the dissolved oxygen. So this is the oxygen which is dissolved in the plasma portion, the water content of the plasma. So the oxygen is going to be dissolved in the plasma portion of the blood. And the hemoglobin bound oxygen, so this is chemically bound oxygen, so the combined oxygen with hemoglobin, that is the hemoglobin bound oxygen. So oxygen is transported by two method, but between these two method, remember that most of the oxygen is transported in the arterial blood by hemoglobin bound method or combined oxygen with hemoglobin, and only 1% of the total oxygen is carried in the dissolved form. Now I told you that what is the meaning of the dissolved oxygen. So the dissolved oxygen is that oxygen which is present in the plasma portion or the water portion of the blood. So the dissolved oxygen amount, remember here that the amount of dissolved oxygen, I am writing here DO2, D stand for dissolved oxygen, depends on a law which is known as HENRY apostrophe S. Okay, Henry's laws. So Henry's law is saying that dissolved oxygen directly proportional to the partial pressure of oxygen in the arterial blood. So according to this law, the dissolved oxygen content of the arterial blood will be 0.003 multiplied by partial pressure of oxygen in the blood, partial pressure of oxygen in the blood. So remember this formula. So the formula is partial pressure of oxygen multiplied by this 0.003. What is this 0.003? This 0.003 is a constant. This depends on the solubility coefficient of the oxygen. So this 0.003 is the solubility coefficient of the oxygen multiplied by partial pressure of oxygen in the blood. That will give you the total content of dissolved oxygen in the blood. So if you think of the arterial blood dissolved oxygen, think separately arterial blood dissolved oxygen and venous blood dissolved oxygen. So the arterial blood has a partial pressure of oxygen. What is that? That is PO2, and that is 98 millimeter of mercury. So obviously the dissolved oxygen content in the arterial blood will have a dissolved oxygen content which will be equal to 0.003 multiplied by partial pressure, that is 98 millimeter of mercury, and this will be equal to 0.29 ml. Got it? So if I ask you what is the amount of dissolved oxygen in the arterial blood, your answer will be it is only 0.2 ml per 100 ml of blood, because we are calculating this is 0.003 multiplied by 98 is the partial pressure. So this is the amount of oxygen per deciliter of blood. Getting my point? So same way, if I calculate the venous blood dissolved oxygen content, so the venous blood has a partial pressure of oxygen, and what is that? That is equal to 40 millimeter of mercury, right? 40 millimeter of mercury, 40. So in these cases, the venous blood dissolved oxygen content DTO according to Henry's law will be 0.003, that is the solubility coefficient of the oxygen, multiplied by partial pressure of oxygen in the venous blood, and that is equal to only 0.12 ml of oxygen is present in 100 ml blood. So if I ask you what is the dissolved oxygen content in the venous blood, that is only 0.1 ml of dissolved oxygen is present in 100 ml of blood, and in case of arterial blood, that is 0.29 ml. So from this we can easily understand that the dissolved oxygen content is very low. 100 ml blood is containing only 0.29 ml of dissolved oxygen, but the total oxygen content of the arterial blood is high. So I can easily understand that the maximum oxygen is carried by which format, that is the hemoglobin bound format, or you can say the hemoglobin combined with hemoglobin, chemical bound oxygen. Okay, so hemoglobin bound oxygen depends on, remember, this is very important. Hemoglobin bound oxygen depends on, so if I ask you what is the amount of hemoglobin bound oxygen, you will first say that hemoglobin bound oxygen depends on the saturation of the hemoglobin. So who is carrying the oxygen here? The hemoglobin. So how much saturation the hemoglobin is, that is the condition depends on which the hemoglobin bound oxygen will depends. So saturation of hemoglobin. Now this saturation of hemoglobin, okay, is written as SO2. SO2. S for saturation, O for oxygen. So saturation with oxygen. So this is the hemoglobin saturation. If it is arterial blood, then I will put small a here, and if it is venous blood saturation, then I will put small v here. Now, how to measure the saturation? The saturation of the hemoglobin can be measured by chemically analyzing the blood, and typically this is done with the equipment which is known as the arterial blood gas analysis. You must have heard the radial arterial blood is collected and it is given into a machine, and that machine will give you the value of this SO2, that is the saturation of hemoglobin with oxygen, that is ABG, arterial blood gas analysis. But we have a non-invasive process by which the saturation of the hemoglobin can easily be seen, and that is known as the pulse oximeter. You must have seen the pulse oximeter. So there will be a small clip like equipment will be there which will be put at the fingertip, and that depending on the color of your hemoglobin, it will give what is the saturation of hemoglobin. So if you are calculating the saturation with the help of pulse oximeter, then we use SpO2. So this is pulse oximeter. So SpO2 or SO2, basically both of them are saturation of the hemoglobin with oxygen. But if I am using SpO2, then it is the saturation measured with the pulse oximeter, and if it is SO2, that is the saturation calculated with the chemically analysis of the blood by arterial blood gas analysis. The difference between these two is only 2%. So if you compare the value or reading of these two, the difference is only 2% differences, but the ideal one is the SO2, that is the saturation calculated with the ABG analysis. But whatever, what I told so far is that hemoglobin bound oxygen depends on the saturation of the hemoglobin. Now saturation in turns depends on, okay, now I am writing the second step, that is saturation of hemoglobin in turn depends on partial pressure of oxygen in the blood. So if it is venous blood saturation or if it is arterial blood saturation, what will be the saturation of the hemoglobin? It depends on what is the partial pressure of oxygen in the arterial blood or venous blood. Getting my point? So basically, so far we have understood that this partial pressure of oxygen is basically the determinant of the saturation, and saturation is the determinant of hemoglobin bound oxygen content. Getting my point? Very, very important thing you have to remember, that if the partial pressure of oxygen is changing, then the saturation is also going to change, and if the saturation is changing, then hemoglobin bound oxygen or hemoglobin bound oxygen content is also going to change. So how to calculate this partial pressure of oxygen? Again, the partial pressure of oxygen can be calculated by chemically analyzing the blood in the arterial blood gas analysis, but generally we do not go for this invasive process of ABG, because whenever you attach this pulse oximeter at the tip of the finger, you are getting the estimation of the saturation of hemoglobin, and we know that if the saturation of the hemoglobin is normal, more or less this partial pressure of oxygen in the blood is also normal. So that way you should not calculate the partial pressure of oxygen again and again. Rather, if the saturation is within the normal zone, then we assume that the partial pressure of oxygen is also within the normal range. Okay, but the bottom line is that hemoglobin bound oxygen content depends on saturation, saturation depends on partial pressure of oxygen. If there is decrease in partial pressure of oxygen, so will be the saturation, and so will be the hemoglobin bound oxygen content. So this is very, very important. Now we are going to calculate how much will be the hemoglobin bound oxygen. We are going to calculate based on this understanding which I have already discussed here. So this is the same thing, it is written here, that partial pressure of oxygen is a determinant of the saturation of the hemoglobin, and saturation is the determinant of hemoglobin bound oxygen. Now I will give you some value, and you have to look at those value very carefully. So I am writing here that when the partial pressure of oxygen is 120 millimeter of mercury, when the partial pressure of oxygen is 120 millimeter of mercury, in these cases hemoglobin is fully saturated. That means saturation of the hemoglobin is 100%. And if the hemoglobin is 100% saturation, in these cases 1.39 ml of oxygen will be carried by 1 gram of hemoglobin. 1 gram of hemoglobin. This is very, very important statement. So try to understand here. So when the partial pressure of oxygen, I told you that if the partial pressure of oxygen is changing, then the saturation will also change. So when the partial pressure of oxygen is 120 millimeter of mercury in the blood, then the saturation will be 100%. That means hemoglobin will be fully saturated. If the hemoglobin is fully saturated, then 1 gram of hemoglobin can carry how much of oxygen? 1.39 ml of oxygen will be carried by 1 gram of hemoglobin. But in these cases, you have to understand the hemoglobin that we are talking about is the pure hemoglobin. No impurity will be there. If there is no impurity within the hemoglobin, then the hemoglobin, how much oxygen is going to carry? 1 gram hemoglobin will be carried by 1 gram hemoglobin will carry 1.39 ml of oxygen. This is known as the oxygen carrying capacity of pure hemoglobin. So this is known as the oxygen carrying capacity. Oxygen, okay, carrying capacity of hemoglobin, that is 1.39 ml for pure hemoglobin. But do you think the hemoglobin which is present in our body, which is flowing in our body, that is a pure hemoglobin? Answer is no. Because of this polluted air and because of other factor in the environment, some of the hemoglobin will be combined with the carbon monoxide, that is carboxyhemoglobin, very smaller percentage, but it is there in our blood, normal blood also. And some of the hemoglobin will be in ferric state iron, that is the methemoglobin. So some of the methemoglobin will be there in your blood, some of the hemoglobin will be in the carboxyhemoglobin form. So bottom line is that although we are discussing that 1 gram of pure hemoglobin is going to carry 1.39 ml oxygen, but in real life scenario, pure hemoglobin is not there in our blood. So we have to understand that although we are discussing that pure hemoglobin, if it is 100% saturated, 1.39 oxygen it can carry, but we have to think of the real life scenario. So that's why I'm writing here, in case of real life scenario, 1.3 ml of oxygen is carried by, okay, 1 gram of hemoglobin. So 1.39 ml oxygen is carried by 1 gram of hemoglobin. 1 gram of hemoglobin. This is in a real life scenario. This is in real life scenario. Okay, so this is the word given in Gerong. So in case of real life scenario, okay, in our body, what is actually happening? It is 1.3 ml of oxygen which is carried by 1 gram of hemoglobin, because in our body hemoglobin is not in the purest form. Getting my point? So bottom line so far is that whenever your hemoglobin is 100% saturated, with a saturation of 100%, 1 gram of hemoglobin can carry how much oxygen? 1.34 ml of oxygen, that is in a real life scenario. But saturation is 100%, then and then only 1.34 ml of oxygen will be carried by hemoglobin. But for 100% saturation, how much partial pressure of oxygen you require? 120 millimeter of mercury partial pressure you require. But do you think in arterial blood partial pressure of oxygen is 120 millimeter of mercury? It is not 120 millimeter of mercury. So in case of arterial blood, what is the partial pressure of oxygen? We know that the partial pressure of oxygen is 98 millimeter of mercury. So this is 98 millimeter of mercury. So basically in arterial blood partial pressure of oxygen is 98 millimeter of mercury. Now if the partial pressure is 98 millimeter of mercury, so obviously the saturation will be lesser than that of the 100%, because for 100% saturation I require 120 millimeter of mercury partial pressure. So whenever the partial pressure is 98 millimeter of mercury, the saturation of the hemoglobin will be 97%. Now, if the hemoglobin is 97%, then how much oxygen will be carried by this hemoglobin? Okay, so the hemoglobin, when it is 100% saturated, the amount of oxygen carried by it is 1.34 ml. But when it is 97% saturated, how much will be the oxygen carried by 1 gram of hemoglobin? So, how to calculate that? 1.34 ml if it is 100% saturated. If the saturation is 97%, then how much? So, it will be 1.29 ml of oxygen is carried by 1 gram of hemoglobin. So, in arterial blood, look very carefully. In arterial blood, what is the oxygen carried by 1 gram of hemoglobin? So, in arterial blood, partial pressure of oxygen is 98 millimeter of mercury. Saturation of hemoglobin is 97%. When the saturation is 97%, 1 gram of hemoglobin is carrying how much hemoglobin? 1.29 ml of oxygen. Getting my point? 1.29 ml of oxygen. So, in arterial blood, 1 gram hemoglobin is carrying 1.29 ml of oxygen. But if you think of the venous blood, so let's write here. So, in case of venous blood, what is the partial pressure of oxygen? The same thing we are discussing again and again, 40 millimeter of mercury. Now, if the partial pressure of oxygen in the blood is 40 millimeter of mercury, venous blood obviously, what will be the saturation? Obviously, the saturation will be lower, and that saturation percentage is 75%. When the saturation is 75%, how much oxygen will be carried by 1 gram of hemoglobin? So, simple thing is that 75 upon 100, and it will be 1.001 ml of oxygen is carried by 1 gram of hemoglobin. In case of which blood? In case of venous blood. So, in case of venous blood, for partial pressure of oxygen is 40 millimeter of mercury, saturation of hemoglobin is 75%, 1 gram of hemoglobin is carrying 1.001 ml of oxygen. Getting my point? So, this is very important calculation you have to understand very carefully. So, first we have discussed that if 100% saturation is required, what is the partial pressure, that we have discussed. And if the 100% saturation is there, pure hemoglobin can carry 1.39 ml of oxygen, but impure hemoglobin, or in real life in our body, 1.34 ml oxygen is carried by 1 gram of hemoglobin, provided the saturation is 100%. But saturation is not 100%. So, in the saturation is 97%, 1 gram hemoglobin can carry 1.29 ml of oxygen, and when the saturation is 75%, 1 gram of hemoglobin can carry 1.001 ml of oxygen. Now, with this concept, I am 100% sure that you can easily calculate the total oxygen content of the arterial blood in 100 ml blood. So, what we are going to calculate? We are going to calculate the oxygen content of the arterial blood and venous blood. Content means total amount of oxygen, and we are going to express this oxygen content in 100 ml blood in 1 deciliter in dl of blood. In dl of blood means we are going to calculate this in 100 ml of blood. Getting my point? So, tell me, in 100 ml blood, how much hemoglobin is there? So, hemoglobin normal value is how much? That is 15 gram percentage. Gram percentage means in 100 ml blood, or 15 gram hemoglobin is present in 100 ml blood or per deciliter of blood. And we have just understood, so I will write it's more carefully. So, this is 15 gram of hemoglobin. So, just now we have discussed that 1 gram of arterial blood right here. So, 1 gram of hemoglobin in arterial blood, okay, can carry 1.29 ml of oxygen, and 1 gram of hemoglobin in venous blood can carry 1.00 ml of oxygen. So, whenever we know that the total amount of hemoglobin in 100 ml blood is 15 gram and 1 gram hemoglobin can carry how much oxygen? 1.29 ml. So, I can easily write down here that in arterial blood, hemoglobin bound oxygen will be equal to 1.29 ml is carried by 1 gram of hemoglobin and total hemoglobin is 15 gram. So, 15 gram multiplied by 1.29, it will be 19.8 ml of oxygen will be carried by 100 ml of blood or per deciliter of blood. So, this is the final oxygen content in the form of hemoglobin bound oxygen, that is 19.8 ml of oxygen is carried by 100 ml of blood. But are you forgetting the dissolved oxygen content? Answer is no. Although the amount of dissolved oxygen is very less here, but we have already calculated the dissolved oxygen in the arterial blood is 0.29 ml and dissolved oxygen in the venous blood is 0.12 ml. So, let's again discuss here. So, we have just calculated the hemoglobin bound oxygen in the arterial blood and that is 19.8. So, you have to also consider the dissolved oxygen content. So, the dissolved oxygen content in the arterial blood is 0.29 ml per deciliter of blood. So, what is the total oxygen content of the arterial blood? Total oxygen content of the arterial blood will be addition of this 19.8 plus 0.29. So, it will be 19 point, okay, this will be around 19.5 I believe. So, this will be around 19.5 and this is 19.2. So, total will be 19.8 ml or approximately you can say 20 ml of oxygen per 100 ml of blood. So, this value, this 19.8 or 20 ml, this value is known as the oxygen content of the arterial blood. So, this is the oxygen content of the arterial blood is 19.8 or you can say approximately 20 ml per deciliter of blood. Got it? So, this is the arterial blood oxygen content calculation. So, what about the venous blood oxygen content calculation? So, venous blood we have just calculated, if you look at here, we have just calculated that venous blood 1 gram hemoglobin is carrying 1.001 ml of oxygen. So, hemoglobin is 15 gram. So, the venous blood hemoglobin bound oxygen will be equal to 1.001 multiplied by 15 and this will be simple approximately 15.1 ml approximately. Okay? And we have discussed previously that the dissolved oxygen content of the venous blood is 0.12 ml only. So, the total oxygen content of the venous blood is equal to 15.2 ml, 15.2 ml, and this is known as the oxygen content of the venous blood. Okay, so approximately 15 ml. So now you understood the oxygen transport by the arterial blood, that arterial blood oxygen transport 100 ml blood transport 20 ml of oxygen, approximately 20 ml of oxygen, and in case of venous blood 100 ml of venous blood is transporting how much ml of oxygen? 15 ml of oxygen. Getting my point? So, this is the bottom line that you have to understand. So, if you look at this, so what we have understood so far, we have understood that oxygen is carried by two format, dissolved and hemoglobin bound. Okay, first we have calculated the dissolved oxygen content and then we have calculated the hemoglobin bound oxygen. So, whenever we was calculating hemoglobin bound oxygen, we first calculated that how much oxygen is carried by 1 gram of hemoglobin and then we have multiplied that value with total amount of hemoglobin, right? And this way we have calculated that what is the normal oxygen content of the arterial blood and what is the normal oxygen content of the venous blood. So, 20 and 15. So, what is the difference between these two values? 5 ml. So, basically in this schematic diagram what I want to show here, suppose the arterial blood is coming through here. So, the arterial blood, okay, is coming through here and this is the venous blood. Just now we have understood that arterial blood oxygen content is approximately 20 ml of oxygen is there in 100 ml of blood or per deciliter of blood, and in case of venous blood 15 ml of oxygen is there per deciliter of blood. So the difference between this is known as the artery venous oxygen difference. So the artery and venous oxygen difference is 5 ml. So what is happening to that 5 ml of oxygen? We all know that 5 ml of oxygen is delivered to the 5 ml of oxygen per deciliter of blood is extracted at the level of tissue. So the tissue is extracting. So this is the extraction of the oxygen by body tissue. So arterial blood is supplying the oxygen to the level of tissue. Tissue is taking 5 ml of oxygen from 100 ml of blood which is going through the tissue level. So if the 100 ml of blood is going to the any tissue, then tissue can extract 5 ml of oxygen. So from here you have to understand what is the meaning of oxygen extraction ratio, because that has been asked in MCQ. So oxygen extraction ratio is calculated by, okay, consumption upon supply, consumption upon supply of oxygen. So how much oxygen is consumed by the level of tissue? Tissue is consuming only 5 ml of oxygen. So this is 5 ml. And how much supply you are giving? The supply is given by the arterial blood. How much oxygen supply you are giving to the level of tissue? 20. So 5 upon 20, that is 1/4, or this is approximately 25%. So this has been asked in MCQ. So the oxygen extraction ratio at the level of tissue is 25%. So this is very easy. So now I hope you have understood that how the oxygen is transported in the arterial blood. So now I am going to give you a summary whatever we have understood so far. So we have already told you multiple times that the partial pressure of oxygen in the alveoli is 100 millimeter of mercury. Okay, so with this partial pressure of 100 millimeter of mercury, if you look at the arterial blood partial pressure, that is 98 millimeter of mercury. So suppose the blood is circulating in this direction, it is reaching at the level of tissue, and then it is converting into venous blood. So this blue color arrow means this is the venous system. Okay, so this is the venous side, and the other one, this is the arterial side. So at the level of arterial blood, what are the parameters that we have understood so far? We have already calculated that the partial pressure of oxygen in the arterial blood, we put this small a, this indicate the arterial blood. So the partial pressure of oxygen in the arterial blood is 98 millimeter of mercury. So don't forget this information. Saturation of hemoglobin in the arterial blood, SaO2. So the small a is for arterial blood. So that is 97%. With a saturation of 97%, the total oxygen content CaCO2. So this C stands for content of oxygen, A stands for arterial blood oxygen content. So this is approximately 20 ml oxygen is there in 100 ml of blood. So all this information we have discussed in detail, you have to remember in step-by-step fashion. Due to any reason, if your hemoglobin is less, then the oxygen content will also be lesser. That you can easily understand, because the total oxygen content depends on the amount of hemoglobin and how much oxygen is carried by 1 gram of hemoglobin. Same way, if you write down the parameter in the venous blood, so the venous blood has a partial pressure of oxygen PbO2, which is 40 millimeter of mercury. With a partial pressure of 40 millimeter of mercury, what will be the saturation of hemoglobin in the venous blood? I already told you that is 75% saturation. With a saturation of 75%, CvO2, venous blood oxygen content, is approximately 15 ml per deciliter of blood. So remaining 5 ml oxygen has been delivered at the level of tissue. So this is known as the oxygen extraction by the tissue, and that is ratio is calculated, that ratio is 25%. So this is the summary of the oxygen transport. Now after understanding the oxygen transport, you have to understand the oxygen hemoglobin dissociation curve. Oxygen hemoglobin dissociation curve is very simple. Whatever we have discussed so far, that is plotted in graphs, and that is known as oxygen hemoglobin dissociation curve. So what we have learned so far, I told you that if your partial pressure of oxygen is changing, then the saturation of hemoglobin will also change, and this relationship has been plotted in the oxygen hemoglobin dissociation curve. So that's why x-axis is the partial pressure of oxygen and y-axis is the saturation of the hemoglobin. Now tell me certain number, that if the partial pressure of oxygen is 100, if the partial pressure of oxygen is 120, okay, so I'll write here 120, then how much will be the saturation of hemoglobin? 100% saturation will be there. If the partial pressure of oxygen in the blood is 98 millimeter of mercury, then hemoglobin will be 97% saturated. If it is 40 is the partial pressure, then how much is the saturation? 75%. And if the partial pressure is 0, then the saturation will also be 0. Now, based on this 4 number, if you plot a curve, the curve will look like a sigmoid shaped curve. Okay, so I'll draw this curve first, then I will explain. Okay, so look at this. So this is a kind of sigmoid shaped curve which is explaining that initially when the partial pressure of oxygen is rising, the saturation is also rising, but that rise is not very significant. But later on this rise is very steep, and at the end there is a plateau. So this plateau means saturation cannot increase beyond this point. That is the maximum saturation. Getting my point? So this highlighted portion here, this is the flat portion, plateau portion. Plateau portion means saturation cannot be increased beyond this point. So what is the saturation at this point? So this is fully saturation of hemoglobin. That means that is 100% saturation. And I told you for 100% saturation how much partial pressure of oxygen is required. So if I drop a perpendicular from here, okay, so this perpendicular will give you, so I am dropping a perpendicular, this perpendicular will give you that if you require 100% saturation, how much partial pressure of oxygen is required? 120 millimeter of oxygen partial pressure is required. Okay, so this is 100% saturation. So I will plot here. So this is my scale. So with this scale, if I plot this saturation here, this will be how much saturation? This will be 100% saturation. So I'll take this pen. This is 100% saturation. So now this is 50%, this is 75%. So this is 75% saturation, this is 50%. So this is 50%, and this is 25%, and this is 0% saturation. Okay. So for 75% saturation, so suppose if I drop a perpendicular from this 75% saturation, okay, on this curve, and from there if I drop another perpendicular on this x-axis, okay, so this is the partial pressure of oxygen which is required for 75% saturation. Could you recall what was the value for 75% saturation? How much you require the partial pressure of oxygen? That is 40 millimeter of mercury. Okay, and 50% saturation, how much partial pressure is required? That is very important. So I am dropping on perpendicular from this 50% on this curve, and from there if I drop another perpendicular on x-axis, so 50% saturation of hemoglobin require a partial pressure which is around 26 millimeter of mercury. So this 50% saturation require how much partial pressure? 26 millimeter of mercury. This important information you have to remember. This is known as P50 of hemoglobin. P50 of hemoglobin is generally ranges from 23 to 26 millimeter of mercury. So here I have written 26 millimeter of mercury, but it has a normal range of 23 to 26 millimeter of mercury. So what you are finding out here, that the oxygen hemoglobin dissociation curve is a sigmoid shaped curve, and then at the end of the sigmoid shape there is a plateau. So sigmoid shaped curve means that initially the saturation of hemoglobin with oxygen is very difficult, but later on there is a steeper portion, and then there is a plateau. Now this kind of sigmoid shaped curve, why the saturation is sigmoid, following a sigmoid shaped curve? Because of the property of the hemoglobin, and that property is known as the cooperative binding property of hemoglobin with oxygen. Cooperative binding property, okay, property of hemoglobin with oxygen. What is the meaning of the cooperative binding property of oxygen with hemoglobin? So hemoglobin contain two alpha chain and 2 beta chains, and the 4 molecule of oxygen can bind with the hemoglobin. So initially the first molecule of oxygen entry into the hemoglobin is very difficult. So suppose these are the globin chain, these are the globin chain, alpha and beta globin chain is there. Okay, so first molecule of oxygen entry is very difficult inside the hemoglobin. So that's why initially the huge partial pressure is required for little amount of saturation. But whenever one oxygen enter inside the hemoglobin, the remaining oxygen can easily enter inside the hemoglobin. So what is the meaning? Means first oxygen entry is very difficult, but whenever one of the oxygen is entering in the hemoglobin, it is causing relaxation of the hemoglobin so that the remaining oxygen is easily entering. So that's why initially it is very difficult to saturate the hemoglobin with oxygen, but whenever some amount of saturation is happening, later on the saturation increases to a very high level. So this kind of property is known as the cooperative binding property of hemoglobin with oxygen, and because of the cooperative binding property, the oxygen hemoglobin dissociation curve is which shaped? Is sigmoid shaped. Okay, and with this oxygen hemoglobin dissociation curve, we have already know the information that if the saturation is 100%, partial pressure is 120. If the saturation is 97%, partial pressure is 98. Partial pressure of 40 means saturation will be 75%. Now we have understood another term that is known as the P50 of hemoglobin. What is P50 of hemoglobin? P50 of hemoglobin means 15% saturation of hemoglobin require what partial pressure, and that we have already discussed, that is 23 to 26 millimeter of mercury. So P50 value of hemoglobin, you should not forget, 26 millimeter of mercury partial pressure of oxygen require for 50% saturation of hemoglobin. Now, sometimes this oxygen hemoglobin dissociation curve can be shifted on the right hand side, means it can shifted in this side, this will be known as the right hand side shifting, or the curve can be shifted on the other side, that will be known as the left hand side of shifting. So if the curve is shifting on the right hand side, so the shape of the curve will remain as it is, but the curve will shift parallelly on the right hand side. So this is known as the right hand shifting of the curve. Okay, so this is known as the right sided shifting, right sided shifting of the curve. Okay, and if the curve is shifting on the other side, so in this, so the maintenance of the curve is there, I mean maintenance of the shape of the curve is there, but the curve is shifting on the other side, so this will be known as the left hand side. Now we are going to understand that what is the meaning of this right hand shifting of the oxygen hemoglobin dissociation curve, and what is the causes of this right hand shifting curve. Okay, so right sided shifting of the oxygen hemoglobin dissociation curve, right shifting of OHDC. So what is the meaning of this? So meaning of right hand shifting is that there is increase in P50. So P50 value of hemoglobin increases. Okay, increases. Why? Look at, so if the curve is shifting on the right hand side, in these cases if I ask you calculate the P50 of the hemoglobin in case of right hand shifted curve, in this curve if you calculate the P50, so what you have to do, from this 50% saturation you have to drop a perpendicular on this shifted curve, and from there you have to drop on another perpendicular on the x-axis. So I can easily understand that the P50 value, which was earlier it was 26, now this value has increased to a different point. So that's why we say that P50 value will be increased in case of right shifting of the oxygen hemoglobin dissociation curve. So right hand shifting means P50 value increases. Now, what is the literal meaning of the increased P50 value? What is the meaning of this increased P50 value? Increased P50 value means for the same 50% saturation, you require higher partial pressure of oxygen. Getting my point? Initially, 50% saturation was requiring 26 millimeter of partial pressure of oxygen, but now for the same amount of 50% saturation, you require higher amount of pressure to be given. That means hemoglobin is taking oxygen easily, or hemoglobin not taking oxygen easily? Hemoglobin is not taking oxygen easily. It is difficult to saturate. That's why you have to give more pressure, and then only you will get the equal amount of saturation. So right hand shifting means first significance is that P50 value will increase. Increase P50 value means what happens to the oxygen affinity of hemoglobin? Oxygen affinity of the hemoglobin has been reduced. Oxygen affinity of the hemoglobin has been decreased. Getting my point? So oxygen affinity reduces. And the third is that if there is decrease in the oxygen affinity of the hemoglobin, okay, so what will happen? The hemoglobin will carry the oxygen to the level of tissue, and at the level of tissue, it will find out that the tissue partial pressure of oxygen is very less. So now the hemoglobin will get the chances to release the oxygen to the level of tissue easily, because hemoglobin has less affinity for the oxygen. If there is less affinity, means hemoglobin will try to release the oxygen as soon as possible, because it has no strong bonding, low affinity, decrease affinity. So decrease affinity means hemoglobin will easily release the oxygen to the level of tissue. This kind of release of oxygen to the level of tissue is known as the unloading of oxygen. So unloading of oxygen, from hemoglobin will be easier or difficult? It will be easier. Okay, it will be easier, or you can say it will increased. Okay, so release of oxygen at the level of tissue will increase. So please remember that these three important significance of right hand shift. Right hand shift means P50 will increase, oxygen affinity will decrease, and release of oxygen to the level of tissue will also increase. Now, what are the causes of this right shifting? So whenever you get the meaning of the right shifting of the curve, you will try to understand that what are the causes. So first cause you remember like this, that due to any cause, if there is increase in body temperature, suppose a person is doing exercise, so during exercise there will be production of the heat, and because of the production of the heat there will be increase in body temperature. Increased body temperature will causes right shifting of the curve. So the right shifting of the curve means what will happen, the tissue will get more oxygen, because more oxygen will be easily released at the level of tissue due to this increased body temperature. Now try to imagine the other point like this, that if there is increase in body temperature, what is going to happen? What will happen to the metabolism of the tissue? So the metabolism of the tissue is going to increase. So increased metabolism means what will happen to the carbon dioxide production? So increase carbon dioxide production. So whenever there is increased carbon dioxide production, we know that there will be increase in partial pressure of carbon dioxide in the blood. So increased carbon dioxide or hypercapnia is also a cause of the right shifting of the curve. Now, if there is increased carbon dioxide production, so the carbon dioxide will react with water due to carbonic anhydrase enzyme, and more H plus ion will be produced. More H plus ion means there will be acidosis. So increased H plus ion or acidosis is also a cause of right shifting of the curve. So increased temperature, increased carbon dioxide or hypercapnia, and increased H plus ion or acidosis. Now, if there is right shifting of the curve only due to carbon dioxide increase or H plus ion, then this right shifting is also known as Bohr's effect. So this is also known as BOHR apostrophe S, Bohr effects. Okay, so this Bohr effect you will understand more in carbon dioxide transport chapter, but for the timing remember that if the oxygen hemoglobin dissociation curve is shifting on the right side either due to increase H plus ion or due to increased carbon dioxide, then that kind of right shifting which is happening either due to carbon dioxide or H plus ion, that kind of right shifting of the HDC curve is also known as Bohr effect, right? But if the curve is shifting on the right side due to increased temperature, that is not Bohr effect. And I will write down another cause of right shifting that is very important, that increase 2,3 DPG, diphosphoglycerate or biphosphoglycerate in the RBC. So RBC, mature RBC contain huge amount of 2,3 BPG or 2,3 DPG, whatever you say, diphosphoglycerate or biphosphoglycerate. If the content of the 2,3 DPG inside the RBC is high, more the higher content, more will be the right shifting of the oxygen hemoglobin dissociation curve. So there are 4 causes I have written here which will causes right shifting of the oxygen hemoglobin dissociation curve. If the curve is shifting on the right side only due to carbon dioxide and H plus ion, that is known as the Bohr effect. But if the curve is shifting on the right hand side due to this 2,3 DPG production or increased temperature, that is not the Bohr effect. Got it? So now we will try to understand that what are the causes of increased 2,3 DPG production inside the RBC, so that right shifting is going to happen. So now we are concentrating on this 2,3 DPG. Multiple MCQ has been asked from this topic. So 2,3 DPG is produced inside the RBC by a bypass pathway from glycolysis, and that bypass pathway all of you know known as Lewis-Rappaport pathway. Okay, Lewis-Rappaport pathway. So this pathway is producing 2,3-DPG inside the RBC, and this is a bypass pathway from glycolysis. So as you can see here, all this product that I have written here, this is the pathway for glycolysis. So from it will start from the glucose and it will end at the level of pyruvate. Okay, in between there are multiple steps, but I have not written because that path of the glycolytic pathway you know from your biochemistry knowledge. Now this glycolytic pathway is going on, but there is a bypass pathway from this glycolysis where this 1,3-bisphosphoglycerate will produce 2,3-DPG with the help of the enzyme biphosphoglycerate mutase. So this mutase enzyme is very, very important to be remembered. So mutase enzyme that is converting this 1,3-biphosphoglycerate into 2,3-biphosphoglycerate, or this is our 2,3-DPG diphosphoglycerate. Getting my point? And then this 2,3-DPG will be broken down to the 3-phosphoglycerate by the enzyme, and that is known as which enzyme? Phosphatase enzyme. So mutase enzyme is causing formation of the 2,3-DPG inside the RBC. So more mutase activation means more will be the production of the 2,3-DPG, and more phosphatase means this 2,3-DPG will be decreased inside the RBC. And I told you already that if the content of this 2,3-DPG is increased inside the RBC, then what will happen? What kind of shift is going to happen? Right shift is going to happen. Now here you remember that chronic acidosis is an inhibitor of enzyme mutase. So if chronic acidosis is there, then mutase enzyme will be inhibited, and if the mutase enzyme is inhibited, what will happen to the production of the 2,3-DPG? It will decrease. And if there is decreased production of 2,3-DPG, what kind of shift is going to happen? So if there is increased production of 2,3-DPG, then there is right shifting. Okay, we have discussed here, then there is right shifting. But if there is decrease in production of the 2,3-DPG, so obviously there will be left shifting. So this acidosis can causes left shifting of the curve because of the decreased 2,3-DPG production. But what we have already discussed so far, that acidosis is a cause of right shifting of the curve. So please remember that acidosis by direct effect, it causes which kind of shifting? Right shifting of the OHDC curve, right shifting of the OHDC curve. Okay, right shift of OHDC. But by indirect effect, what is the indirect effect? By reducing the 2,3-DPG content, it can also causes left shifting of the OHDC curve, So what is the bottom line? Bottom line is that if the acidosis is acute, then the direct effect is going to prominent. But if the acidosis is chronic in nature, okay, so here I am writing chronic in nature, then what will happen? It can causes decreased production of 2,3-DPG, and in that cases left shift is going to happen. So if the question is acidosis causes which shift, your answer will be right shift. But suppose I am saying that you have kept the RBC in acidic solution for long duration, maybe 1 week, maybe 2 weeks, that is the storage of blood in blood bank. We generally store the blood in the acidic solution. So that is a kind of chronic acidic condition for the RBC. So whenever you store blood in chronic acidic condition, what will happen? 2,3-DPG production will be less, and what kind of shift is going to happen? Left shift. That's why we know that storage blood means there will be left shifting of the oxygen hemoglobin dissociation curve. Getting my point? So this is very, 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 very important that you have to remember. Now I told you again and again that 2,3-DPG increased production means there will be right shifting. Now if I ask you, what are the causes of increased 2,3-DPG production? What are the causes of increased 2,3-DPG production? So here the causes has been written. The causes of increased 2,3-DPG production, so means all these causes is going to causes which kind of shift? It is going to causes right shift. So what are the cause? The causes has been written here, that chronic hypoxia. So chronic hypoxia, the typical example is if you are ascending into high altitude condition, so the chronic low grade hypoxia will be there. So in high altitude, what shift is going to happen? Right shift is going to happen because of increased 2,3-DPG production. During exercise also there is increased production of 2,3-DPG. So I told you earlier that if the person is doing exercise, there will be increase in temperature also, and there will be increase in 2,3-DPG production also, and both of them are the causes of the right shift. So during exercise the right shift is going to happen, but this increased temperature is the main factor, because 2,3-DPG may or may not increase depending on the training of the person. Okay, so exercise causes right shifting of the OHDC curve by increased 2,3 DPG production and increased temperature. Any kind of anemia, if it is there, then it will also causes right shifting by increasing the 2,3 DPG content of the RBC. Hormone, certain hormone, if it is increased, means if there is increased thyroid hormone in the body, thyrotoxicosis, okay, hyperthyroidism, increased growth hormone, acromegaly, or increased androgen, if these hormones are high in blood, then also 2,3 DPG production will be increased, and 2,3 DPG production increase means right shift is going to happen. Rise in body temperature, we have already seen that rise of body temperature can directly causes right shifting of the curve. Not only that, it can also causes increased 2,3 DPG production. And if the iodine, pyruvate or phosphate content of the RBC increased, if the content of iodine, RBC content of iodine, pyruvate or phosphate is increased, then also 2,3 DPG production will be higher and right shift is going to happen. So again and again I am saying 2,3 DPG more means right shift. Why? Question is why? Why the 2,3 DPG will causes right shifting? Now to understand this thing, you have to understand 2,3 DPG binds with hemoglobin, how it binds with hemoglobin. Okay, and how many molecule of 2,3 DPG binds with hemoglobin? So hemoglobin contain 2 alpha chain. So suppose this is alpha chain and 2 beta chain. What do you think? 2,3 DPG binds with which chain of hemoglobin, alpha chain or beta chain? Globin chain I am talking about. Okay, so suppose the oxygen is attached with the alpha chain also. Okay, so oxygen is attached with beta chain also. If the oxygen is attached with both alpha and beta chain, then 2,3 DPG is not going to bind with this hemoglobin. Getting my point? So this is the structure of hemoglobin. We are trying to understand how the 2,3 DPG is causing right shifting. So first of all, you require partial deoxygenation of this beta chain partially. Okay, so first this beta chain should release their oxygen. So I am writing the first point. For 2,3 DPG binding, hemoglobin should be partially deoxygenated. Partially deoxygenated hemoglobin. Oxygenated hemoglobin is required for 2,3 DPG binding. Getting my point? If the hemoglobin is fully saturated with oxygen, 2,3 DPG is not going to bind. Then this beta chain, both the beta chain, they are going to create a pocket. Okay, so alpha chain is there, beta chain is there. In three-dimensional structure, if you look at, there is a pocket created between these two beta chain because these are the protein. So if you look at the coordinate structure of the protein, there will be kind of pocket in between two beta chain. And at the surface of this beta chain, there will be positively charged amino acid. There will be positively charged amino acid. Now, if you look at the 2,3 DPG, this 2,3 DPG molecule, on the surface of this 2,3 DPG molecule, there is presence of negative charge. So, the 2,3 DPG can easily fit into this pocket created by both the beta chain. Why? Because this 2,3 DPG contain negatively charged on its surface. With help of this negatively charged, it can easily attach with positively charged amino acid on the surface of this beta chain, and because of this negative positive interaction, the pocket created by both the beta chain can easily fit one molecule of 2,3-DPG. Getting my point? So the second point that we have understood from here, that 2,3-DPG binds with which chain of hemoglobin? 2,3-DPG binds with which chain of hemoglobin? Beta chain of hemoglobin. It cannot bind with the alpha chain, it cannot bind with any other chains of hemoglobin. And how many molecule of 2,3-DPG binds with one molecule of hemoglobin? We have understood here that only one molecule of 2,3-DPG can fit into the pocket created by both the beta chain. So both the beta chain is required for binding of one molecule of 2,3-DPG in hemoglobin, and alpha chain cannot bind with 2,3-DPG. So total amount of 2,3-DPG that binds with one molecule of hemoglobin is only one. So that's why there is an MCQ in AIIMS, that what is the molar ratio of 2,3-DPG and hemoglobin. Hemoglobin is to 2,3-DPG. Okay, it will be 1:1. Very important point. So the molar ratio is 1:1 for hemoglobin is to 2,3-DPG. So whenever 2,3-DPG binds with hemoglobin, okay, it stabilizes the low affinity state of hemoglobin. So far we are discussing how the 2,3-DPG is binding. So after 2,3-DPG binds with this deoxygenated beta chain, it will causes stabilization of the low affinity state of hemoglobin, means the remaining oxygen which is attached with this alpha chain, it can be easily released from hemoglobin. Easy easy release of oxygen from hemoglobin. Why? Because this 2,3-DPG causes stabilization of, okay, it causes stabilization of low affinity state of hemoglobin. Low affinity state of hemoglobin means hemoglobin has low affinity for the oxygen after binding with 2,3-DPG. Now, low affinity binding with oxygen means hemoglobin will easily release the oxygen to the level of tissue, and if the hemoglobin has low affinity for the oxygen, if the hemoglobin is easily releasing the oxygen to the level of tissue, then what kind of shift is there? That is right shift. So that's why we say that 2,3-DPG after binding with the partially deoxygenated hemoglobin, it causes stabilization of the low affinity state, means hemoglobin cannot go for the high affinity state, it will remain in the low affinity state. Low affinity state means all the oxygen which is still attached with the alpha chain, they will be easily released at the level of tissue, and that is nothing but your right shift. So now I hope you got that what are the causes of the right shifting of the curve, and what are the causes of the increased 2,3-DPG production, and how 2,3-DPG production causes right shifting of the OHDC. Got it? Okay. So now this is all about the right shifting. Okay. Now we are coming to the left shifting of the curve. So if I ask you what is the causes of the left shifting of the curve, so easily you can tell me some of the causes, because we have already seen that if there is increased temperature, then there will be right shifting. So if there is a decrease in temperature, hypothermia, so obviously there will be left shifting of the curve. If there is decreased H plus ion or alkalosis, then also there will be left shifting of the curve. Or if there is decreased carbon dioxide in the arterial blood, okay, hypocapnia, then also there will be left shifting of the curve. So that is easy to understand. But apart from these causes, you have to remember certain important causes which has been asked in MCQ. Like for example, fetal hemoglobin, there is left shift, storage of blood, there is left shift, carbon monoxide poisoning, met hemoglobin, and thalassemia. All of these causes left shifting of the oxygen hemoglobin dissociation curve. Now here I have kept the curve already. Okay, so first you look at the normal curve, normal adult hemoglobin curve. So this pink color highlighted, this is the normal adult hemoglobin curve. So the sigmoid shaped curve you can easily find out. In case of fetal hemoglobin, there is left shifting. So look at the fetal hemoglobin curve. The shape of the curve has not been changed here, but the curve is shifting on the left hand side direction. So if the curve is shifting on the left hand side direction, we normally know that for adult hemoglobin, what is the P50 value? Again, look at the P50 value, that is 26 millimeter of mercury. But for the fetal hemoglobin, the P50 value will be, okay, so I'm writing here, for the fetal hemoglobin, okay, so the P50 value will be lesser. P50 value is 19 millimeter of mercury. So for adult hemoglobin, this is 26 millimeter of mercury, and for fetal hemoglobin, that is 19 millimeter of mercury, and the shape of the curve is not altered. Now we can find out another two curve. One is the myoglobin curve. So this is known as the rectangular hyperabolic curve, although it is looking like that it is left shifting of the curve, but that is not actually left shifting. The myoglobin is, the curve is typically rectangular hyperabolic shaped. Why it is rectangular hyperabolic, you will understand. And the carbon monoxide poisoning, it also causes left shifting, but as you can see here that among all of this left shifting, the maximum left hand side shifting is happening because of this carbon monoxide poisoning. So now we are going to understand what is the cause of the left shifting in case of fetal hemoglobin. So fetal hemoglobin contain which chain? 2 alpha chain is there and 2 gamma chain is there. Can gamma chain or alpha chain binds with 2,3-DPG? Answer is no, because 2,3-DPG binds with only the beta chain. So no 2,3-DPG binding in this hemoglobin. Now if the 2,3-DPG binding is not there with the hemoglobin, means 2,3-DPG content is very less. What kind of shift is going to happen? So less 2,3-DPG means left shifting. And because of the left shifting, fetal hemoglobin has higher affinity for oxygen, because I told you that what is the meaning of the right shifting? Low affinity state. What is the meaning of left shifting? High affinity state. So, the hemoglobin has higher affinity for oxygen. That is true for which hemoglobin? Fetal hemoglobin. Why high affinity? Because of the left shifting. What is the cause of left shifting? Because fetal hemoglobin cannot bind to 2,3-DPG. Getting my point? So, fetal hemoglobin has high affinity, that's why left shifting? No, 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 no. Fetal hemoglobin, there is left shifting because of the decreased 2,3-DPG binding, and because of the left shifting, the fetal hemoglobin has high affinity for oxygen. Now, coming to the storage of blood, already I told you that during storage of blood, acidic solution is generally used and low temperature is used. In both of these condition, the ultimate thing that is going to happen in storage of blood, that there will be decreased production or decreased 2,3-DPG content of the RBC, and that is why there will be left shifting. The detail will be discussed in the next slide. In case of carbon monoxide poisoning, so whenever carbon monoxide binds with hemoglobin, okay, remaining oxygen which are already there in the hemoglobin, it will not be able to released from the hemoglobin. So, what I told, suppose the hemoglobin is already attached with oxygen, okay. Whenever the carbon monoxide is entering in the hemoglobin, the oxygen which was already there, those oxygen will not be able to release after carbon monoxide binding. That means the oxygen which is already there, they are becoming high affinity state, and high affinity state means which kind of shifting? That is left shifting. That is why we say that upon binding of the carbon monoxide, the oxygen become high affinity state with the hemoglobin. And not only that, carbon monoxide also decreases 2,3-DPG binding with the RBC. So, these are the two causes of left shifting in case of carbon monoxide poisoning. In case of methemoglobin, I hope all of you know what is methemoglobin. So, methemoglobin means whenever the oxygen, okay, I mean iron in the hemoglobin is converted from ferrous to ferric state, that is known as a methemoglobin. Methemoglobin, whenever the hemoglobin is converted into ferric state, then the oxygen which was already attached with hemoglobin, those oxygen will not be able to release from hemoglobin. Similar kind of scenario like that of the carbon monoxide poisoning. So, that is why we say methemoglobin means the oxygen which are still attached with the hemoglobin, they will be converted into higher affinity oxygen, and there will be left shifting. And thalassemia, for some unknown reason, there is left shifting in case of thalassemia. So, now among all of these causes, we are going to understand that why the storage of blood will causes left shifting, because this has been asked in multiple times in MCQ, and we are also going to understand carbon monoxide poisoning and left shifting. So, whenever you are storing blood, okay, storage of blood generally happens in low temperature. So, storage of blood whenever it is done below 6 degree centigrade temperature, low temperature means it will causes a reduction in the glycolysis process within the RBC. And we have already seen that 2,3-DPG is produced from a bypass from the glycolytic pathway. So, if the glycolysis is reduced, then the 2,3-DPG production is also going to be reduced. So, bottom line is that storage of blood in low temperature means 2,3-DPG will be reduced. And if you are storing the blood in acidic solution, then double problem, because acid is an inhibitor of the mutase enzyme, because I have already told you that it inhibits the mutase enzyme, and because of the inhibition of the mutase enzyme, what is going to happen? There will be further reduction of the 2,3-DPG. So, the bottom line is that because of this point number 1 and because of this point number 2, storage of blood will causes reduced 2,3-DPG content in the RBC. And how much reduction is happen? It is generally seen that if you store blood for 1 to 2 weeks, 2,3-DPG will be zero amount inside the RBC. So, you can easily understand that storage of blood will be left shifting. Left shifting means high affinity of hemoglobin with oxygen, means if you give the storage blood, suppose you have given transfusion to a person with the storage blood. So, storage blood means already the 2,3-DPG is depleted, there is left shifting. Left shifting means hemoglobin will not release the oxygen to the level of tissue. What is the basic purpose of blood transfusion? We give the blood transfusion for better oxygenation of the tissue. But if there is left shifting, then tissue will not get adequate oxygen, because hemoglobin will not release the oxygen to the level of tissue. So, that is why we do not prefer the transfusion of the stored blood into emergency condition, because it will not be able to supply oxygen to the tissue, okay. Because it has been seen that after transfusion, restoration of the 2,3-DPG production will occur, but it will take some time, at least 7-hour time is required for 50% restoration of the 2,3-DPG. So 7 hours is a long time. So if you are giving storage blood, okay, then you know that this storage blood will give oxygen supply properly to the tissue, but for that you require generation of the 2,3-DPG, and at least 7 hours is required for 50% storage of 2,3-DPG production, and within 48 hours 100% replacement of the 2,3-DPG occurs inside the RBC. So these are the information that you should remember, because in MCQ they are asking this question multiple times. So I told you that storage of blood means two problems are there: low temperature and acidic solution. So if we avoid the acidic solution, so obviously the 2,3-DPG reduction will not that much be like that of the acidic solution. So that's why nowadays, rather than ACD, acid cited dextrose, is the solution which was previously used for storage of blood, but for the last few years we are preferring this citrate phosphate dextrose solution for storage of blood. Why? Here the acid is not there, acid citrate phosphate is not there, rather than citrate phosphate dextrose. So in presence of citrate phosphate dextrose solution, the 2,3-DPG reduction or depletion will be lesser in comparison to ACD, acid citrate dextrose solution. So that's why this is the advantage of CPD solution over the ACD solution. So the CPD solution is used nowadays very commonly. So the citrate of this CPD act as an anticoagulant and buffer. The phosphate of this CPD solution increases the 2,3-DPG production, and dextrose also stimulate the glycolytic process. So glycolysis process means there will be more production of 2,3-DPG production. So as you can see here easily, that acid is not there in the CPD, plus this CPD is giving certain stimulant for production of more glycolysis, for production of more 2,3-DPG. So that's why I told you that reduction of the 2,3-DPG in CPD solution is very lesser in comparison to ACD solution. So this you have to remember for your MCQ. Now I told you that carbon monoxide poisoning causes left shifting of the oxygen hemoglobin dissociation curve. Certain point you have to remember about carbon monoxide poisoning, that it has about 250 times more affinity for hemoglobin than oxygen, and carbon monoxide combines with hemoglobin at the same site on the molecule as that of oxygen. Okay, so suppose this is alpha chain, beta chain, beta chain. The oxygen where it is binding, the carbon monoxide will bind with the same places, but after binding of carbon monoxide in the hemoglobin, the oxygen which was attached with the alpha or beta chain, they are not going to be released easily, and that's why I told you that in presence of carbon monoxide, the affinity of the hemoglobin for oxygen is enhanced, and because of this enhancement there will be defective release of oxygen molecule to the tissue, and that is nothing but your left shifting of the curve, left shifting of OHDC. Okay, and because of this, carbon monoxide decreases the oxygen content of the blood also, and that's why there will be hypoxia. It will be understood in the next chapter, hypoxia. Okay, so carbon monoxide and OHDC we understood. Now coming the myoglobin and oxygen hemoglobin dissociation curve. I already told you that myoglobin curve, okay, looks like that it is a left shifted curve, but that is not actually left shifting. Why? Because myoglobin myoglobin binds only one molecule of oxygen rather than 4 molecules of oxygen like that of the normal hemoglobin. So the cooperative binding property is not there in case of myoglobin. I told you earlier that hemoglobin can bind with 4 molecules of oxygen. Initially 1 molecule of oxygen binding is very difficult, but later on it becomes easier, and that is cooperative binding. But because myoglobin can bind with only 1 molecule of oxygen, so obviously cooperative binding of oxygen is not there, and whenever there is entry of 1 molecule of oxygen, suddenly the myoglobin will be fully saturated with oxygen, and that's why you are seeing the curve like this. Okay, you are getting a curve like this, that whenever the oxygen is entering, 1 molecule of oxygen entry means there is almost full saturation of the hemoglobin, and that's why the curve was looking like a rectangular hyperabolic kind of curve. So that's why you have to remember this name, that the shape of the myoglobin curve is rectangular hyperabolic curve. If you compare with the normal oxygen hemoglobin dissociation curve, it will be position on the left hand side of the normal curve, but it is not left hand shifting, rather it is rectangular hyperabolic curve because it binds with only 1 molecule of oxygen. Got it? So this is all about your oxygen transport and OHDC curve. So now let's attempt some of the MCQ. So the first MCQ I explained just now, that cited phosphate dextrose CPD solution is better for hypoxic patient than ACD solution. ACD solution. Why? Because I told you that acid is an inhibitor of the mutase enzyme. So CPD solution is better because it stimulates 2,3-DPG production. So 2,3-DPG reduction in the RBC will be lesser. So there is less decrease in 2,3-DPG in case of CPD solution. This is going to be my answer. Got it? Another question we are going to attempt here. The below graph shows oxygen hemoglobin dissociation curve, the curve marked with A. So as you can find out here, I have shown this curve already, that this is the normal curve given in the question. So any curve which is situated on the left hand side of the curve but maintaining the normal shape of the curve. So this is typical of the fetal hemoglobin. So this C is typical of fetal hemoglobin, right? And this B curve, I told you the shape of the curve is a rectangular hyperbolic kind of curve. So this B curve is a kind of myoglobin curve, and this A curve is the left hand sided shifted curve, and I told you the position of the curve is the subse left. Okay, so left hand side of the curve and the most left hand side position. So this is carbon monoxide poisoning. So curve A has been asked in this question. So this is carboxyhemoglobin or carbon monoxide poisoning. Now we are going to attempt another MCQ. This has been asked in one of the JIPMAR question. Okay, so look at here. A patient developed right to left shunt. Okay, so this question is about the shunting, pathological shunting. Oxygen content of the arterial blood and venous blood is given. So oxygen content of the arterial blood, I am writing CaO2. That is the content of oxygen in the arterial blood. We have already seen. So here it is given 18. Okay, and oxygen content of the venous blood CvO2 is given as 14. This has been given in the question. Oxygen content of the pulmonary capillary is 20 ml per dl. So pulmonary capillary oxygen content is 20 ml per dl. That is the CCO2, oxygen content of the pulmonary capillary. So this C for pulmonary capillary I am writing here, that is 20 ml. Got it? These are the information given in this question. From here you have to calculate the shunt percentage, shunt fraction. So this is a completely different MCQ. To understand this MCQ or to solve this MCQ, you have to understand the shunt fraction. There is a formula. So look at here. What is the shunt fraction? Try to understand. So this is the schematic representation of the lung alveoli. Okay. So this is the venous blood coming here. Okay. Generally, almost all the venous blood should pass through this lung region so that it get proper oxygenation. But because of this right to left shunting, what is happening? Some of this venous blood is directly going towards the arterial side. So basically, this is your shunt and this is your pathological shunt. Getting my point? Okay. So this is your shunt because all the blood should pass through this lung region to get oxygenation. But here I can find out some of the venous blood is directly entering into the arterial side. So this is shunt. Okay. So in this diagram, okay, in this diagram, what we are getting, so this is Q. Q is the amount. Q is the amount. QT, it is the total amount. What is this total amount? This is the total amount of blood. This is the total amount of blood that is flowing through this venous side. Okay. So this is the total amount of blood, QT. So whether the blood is going through this lung or whether the blood is going through this shunt, ultimately all this blood is going to mix up on the arterial side also. So in the arterial side also I am going to get this QT amount of blood. So the amount of blood is remaining same on both sides. But the problem is that one portion of blood is going for oxygenation and another portion is directly going without any oxygenation. So if I ask you what will happen to the oxygen content of the shunt portion, oxygen content of the shunt portion, this will be CvO2. What is this CvO2? You know that CvO2 is the oxygen content of the venous blood. So whatever is the oxygen content of the venous blood, that will be same to same in the shunted blood because it is not getting any oxygenation from the lung. And what is the amount of shunted blood? That is also given here, that is the QS. So from this QT, this is the total volume of blood. QS is passing through this shunt. So the remaining blood will pass through this lung. So what will be the volume of blood that will pass through this lung? That is QT minus QS. I hope you get it. QT that is the total minus shunted blood. That is the amount of blood which is going for oxygenation at the level of lung. So, after oxygenation, what is the content of this capillary blood in the pulmonary region? That is the CCO2. Okay, and what is the content of the arterial blood oxygen? CaO2. So, now I can write down like this. So, if I multiply these two, content of the arterial blood oxygen multiplied by the total amount of blood that is coming here. So, I will get the total amount of oxygen. Okay. So, I am writing here Qt minus CaO2. Okay. So, this is the total amount of oxygen. So, it will be equal to the amount of oxygen that is absorbed here and amount of oxygen that is coming through here. So, if I ask you what is the amount of oxygen in the shunted portion, your answer will be that share Qs amount of blood is flowing through the shunted portion and the oxygen content here is the CbO2. Okay. Plus, what is the amount of oxygen coming from this lung region? So, what is the blood flowing in that lung region? So, Qt minus Qs, already we have calculated that. And what is the oxygen content of this blood? CCO2. So, if I am writing this, so this is the basically your shunt equation. So, what I have written here, Qt multiplied by CaO2 is equal to the Cv multiplied by Qs plus this multiplied by this. So, this is known as the shunt equation. Now, from this equation, if you changes from right side and left side, ultimately you are going to get a formula. This formula is known as the shunt equation. So, what is the shunt equation? Qs, I hope you know, Qs is the shunted portion of blood upon Qt, that is the total volume of blood, CCO2, that is the blood oxygen content in the pulmonary blood, minus CaO2, arterial blood oxygen content, upon your CCO2 minus CbO2. So, if you use this formula, you can easily solve this question. So, what the formula we have just learned? Qs upon Qt is equal to CCO2 minus CaO2 upon CCO2 minus CbO2. So, now here the CCO2 has been given as 20, CaO2 is given 18, okay. So, 20 and CbO2 is given 14. So, basically your Qs upon Qt is this. That means this is 2 upon 6. 2 upon 6 means 1/3. That means I can say that Qs is equal to 1/3 of Qt. Qs is equal to 1/3 of Qt. That means 33% of Qt. So, how much is the blood flowing through this Qs or shunted portion? Qs or shunted portion is 33% of your cardiac output. So, answer here is 33%. Got it? So, this is all about the shunt equation, oxygen transport and everything. Thank you so much.